Good evening, ladies and gentlemen, friends, colleagues. It is a great pleasure to see you face to face in our first public lecture, distinguished public lecture since the pandemic started. So we had quite a long pause, 2 years, since our last face-to-face public lecture. And meanwhile, we had online public lectures, but this is our first face-to-face. And I forgot to tell who I am. I'm Professor Andres Velendowski. I'm head of School of Mathematics and Physics of this university, which organizes and hosts those events. Our distinguished public lecture tonight is Isaac Newton 2022 annual lecture. We're very pleased that our speaker is Professor Charles Leedham-Green, who's here, who is also our external advisor. He's on our school advisory board. Charles' scientific interests are very close to what we do in mathematics in our school. His research in the field of algebra, and in particular in the field so-called group theory, is very close to our Charlotte Scott Research Center in Algebra in the University of Lincoln, led by Professor Huchro, who is also sitting here in the audience. And Charles and Evgeny are long collaborators since quite many years. A few more words about Charles, although I'm sure when you book your ticket you read a short biography, but nonetheless some might skip. Charles is graduate from University of Oxford, both in his undergraduate as well as doctorate degree. And from 1997, he is professor in Queen Mary, University of London. He published many scientific articles, as well as a monograph in his field. And the topic of lecture tonight is very special. Charles completed a translation of basically Newton's book Principia from Latin to English, and I will not say much more. I'll give floor to Charles, who will tell us about this work.
Good. Thank you, Andre. I'm honored to have been invited to give this Newton lecture. My sole qualification for giving the lecture is my translation of Newton's magnum opus, the Principia, or to give it its full title, Philosophiae Naturalis Principia Mathematica. I am a pure mathematician. I am not a historian or an expert in dynamics, astronomy, tidal theory, partial differential equations, theology, or many other topics which Newton treats of. The translation took over 20 years, though of course it took second place to my own research and other academic duties. There you see the first edition as it appeared, and there's my translation, which I'm making too much fuss about. I have also professional connection with the excellent Lincoln Mathematics Department, and especially with Professor Huchro. The Principia is divided into 3 books, and three editions were published in Newton's lifetime, in 1686, in 1713, and in 1725. The latter 2 being serious revisions of what had come before. My translation, in common, I believe, with all others, is a translation of Newton's 3rd edition, though with some references to earlier editions. There have been 2 previous complete and published translations into English. The first, by Andrew Mott, in 1729, which was revised by Cajuri, published in 1934. The second, by Bernard Cohen and Anne Whitman, which was published in 1999. The impulse for the latter apparently sprang from Bernard Cohen's distaste for the Mott-Cajuri translation and the impulse for mine sprang from displeasure at the Cohen-Whitman translation. The second translation of the Principia is a translation into French by Emilie, Marquise du Chatelet, Le Tonnelier de Breteuil. Her translation is accompanied by a brilliant commentary. She was guided by Clairaut. Le Tonnelier de Breteuil, the masculine barrel maker from Breteuil, wasn't a title, it was actually her maiden name. Her title of du Chatelet comes from a marriage, though she preferred actually to live with Voltaire, Voltaire was just his pen name, but that will do, in preference to her husband. She was a leading member of the French intelligentsia and died of the complications of childbirth before her translation was published. And I think, yes, it's a great work. It's a great work. Mathematics, in common with the physical sciences and doubtless other areas of intellectual endeavour, advances not only in the extent of our understanding, but also in the difficulty and depth of the cutting edge. While plotting the courses of the planets around the sun was a very tedious business, I would say that the great bulk of pre-Newtonian mathematics has been taught or could be taught in schools. I would also suggest that the great technical advances that were made before Newton's time did not encourage or use much in the way of mathematical research. Newton's Principia changes all this. Not only does he solve mathematical problems that were completely beyond the grasp of his predecessors, but he also demonstrates for the first time that nature obeys laws that can be expressed mathematically, and that mathematics can then deduce the consequences. Perhaps I should apologize to Galileo and Aristotle and Archimedes. I may have exaggerated there, but they'll forgive me. Voltaire said that philosophers should read the Principia even if they did not understand it. He also stated that the reason that Newton was famous in England was due to the fact that he had a beautiful niece. In fact, I believe it was this beautiful niece who told Voltaire the story of Newton and the apple, which I shall not repeat. There's nothing improper about it, I'm just bored with it. But I have the difficulties that philosophers had in understanding the Principia will have been, to a very serious extent, due to Newton's style of writing. I have the feeling that Newton was writing for God, that is to say, for himself. He computes the mass of Jupiter and the orbits of comets. He develops tidal theory, proves that an oval cannot be rectified by a polynomial equation, and I apologize for the technical terms. He works out the shape of a ship that will minimize resistance, makes great advances in aerodynamics, and so forth. Mathematics and physics were changed forever. But I would claim, with due allowance for exaggeration, that there is no theorem in the Principia that I could not explain, together with Newton's proof, to any research mathematician in less than a quarter of an hour. Newton himself boasted that he could compute any integral in half a quarter of an hour. He computes triple integrals. Later, great mathematicians have led the way in increasing our ambition. When I was a young mathematician, a theorem of great importance was proved, whose proof was regarded as taking 3 years for a specialist to read. This could claim to be one of the most profound theorems ever proved at that time. During my lifetime, the bar has been lifted to a far higher degree. I start my analysis of the Principia with the dynamical laws for which Newton is so famous, the 3 laws of motion and his gravitational law. These laws did not spring unaided from Newton's brain. Anyone with any interest in dynamics has got to read Julian Barbour's brilliant book, The Discovery of Mathematics. But here are the laws. Law 1. Every particle remains in its state of rest or of uniform motion in a straight line, except when it is forced to change its state by forces acting on it. Law 2. The change in momentum is proportional to the momental force that acts and is in the direction in which the force is applied. Law 3. To every action there is an equal and opposite reaction. In other words, the mutual forces between two particles are always equal and are directed in opposite directions. And the law of gravity, the force of gravity between two particles is inversely proportional to the square of the distance between them. The first three laws, the laws of motion, are as stated by Newton with my translation. My choice of particle rather than body as a translation of corpus is a little problematic. It's a technical point that I do not wish to dwell on here. Law 4 is never stated as a law in the Principia, though it plays a very central role. I have said that these did not spring unaided from Newton's brain. In fact, they didn't spring out of his brain at all. None of Newton's of those four laws were in fact original to Newton. They were ideas whose time had come. There is a portrait of Kepler. We're having Kepler's laws, and that, I think, is a genuine portrait of Kepler rather than the bogus one at the top of the Wikipedia page. And there are Kepler's laws of planetary motion. So the planets move in ellipses with the sun at a focus. A straight line from the sun to a planet sweeps out equal areas in equal times as the planet moves around the sun. And the period of a planet, or the length of the planet's year, is proportional to the major axis of the planet's orbit, its length, raised to the power 3/2. It is easy to deduce the inverse square the square law of gravity from Kepler's third law. You should just consider circular orbits, given Newton's first three laws of dynamics. The challenge was to deduce it from the first two laws. So now you've just got a single planet moving, and now, of course, the orbit had better not be circular, because you can't tell how the force varies with distance if the distance doesn't vary. And so here is the diagram for Newton's first proof. So we've got, I don't have a pointer, but it doesn't matter. We've got a planet P moving around the sun S in an ellipse. And Newton has to worry about the curvature at P, hence all this fuss of that part of the diagram. So now, and of course it is sweeping out equal areas in equal times. So there Kepler's two laws in place. So the fact that the planet sweeps out equal areas in equal time means that the force of attraction goes from P to S, from the planet to the sun. That is the law of the conservation of angular momentum. There is Newton's diagram for the conservation of angular momentum. So you've got your planet, and he is proving this by replacing the continuous law of gravitation by a collection of impulses. So it starts at the point A, the planet starts at the point A, gravity has been turned off, so that it moves in a straight line to B, and then gravity suddenly pulls it back and so straight line and a jerk, and then he's going to let the intervals get less and less and take the limit and end up with the conservation of angular momentum, which nowadays we can do in half a line. But this is Newton's proof, and there's an enormous amount of totally incompetent commentary on it. It's really awful. But anyway, that's how it is. And it's not so easy to fill in the gaps, to be honest. Right. Let's go back to here. So the force is determined then by the period of the planet, the length of the year, and the curvature at the point P. And for non-mathematicians, the curvature just says how curved the curve is. So if you turn off gravity, the curvature is 0, and it will just zoom along the straight line from Z to P to R. So in order to work this out, the first thing you're going to have to do, it would seem, is to work out what a formula for the curvature. Well, there is a formula, it's a bit complicated, and then you've got a nasty calculation to do. So I suspect that any mathematicians in the audience who have not taught elementary celestial mechanics would need a fair amount of time and effort to work this out. Is there a better way? A mathematical trick. When faced with a difficult problem, try solving an easier problem first. So, how are we going to make this easier? Well, let's move the sun from the focus to the center. There, that's simpler, isn't it? So now let's just reverse the problem and assume that the force is now directly proportional to the distance. Not inversely proportional to the square, but directly proportional to the distance. If that is the case, then I haven't got a pointer, never mind. We can resolve the force. The force is going from P to C, but we can assume we can split it up into a vertical force and a horizontal force. And because the force is directly proportional to the distance, the horizontal force is proportional, the vertical force is proportional to the vertical distance, the horizontal force is proportional to the horizontal distance, and we can solve two one-dimensional problems at the same time and superimpose them. For the one-dimensional problem, there's no curvature to worry about. It's simple harmonic motion, and the solution is expressed in terms of sines and cosines. When you impose two of these on each other, it goes round in an ellipse. Let me show you how it works then. I should have got this out sooner, but there you go. I may have to stand on the desk. No, I can not. So, if I swing this to and fro, and the period is approximately independent of the amplitude. So if I take a smaller amplitude, it still takes as long to go from one place to another. Okay. Now, if I let it move in 2 dimensions, it is now executing an ellipse. Okay, because the force is proportional to the displacement and is aiming at the point under my thumb. Right. So now we've solved the easy problem. How does that help us with the difficult problem? Well, you see, when you move the center of force from C to P, from C to S. And there's just some fairly simple geometry to see what change that makes in the force required to keep the particle in the same orbit. And the genius point is that by the easy case and the difficult case have the same curvature. So the curvature cancels out and the proof becomes remarkably easy. There it is. I hope I've got this too small for you to be able to read it. But the Newton's proof consists of 7 lines. I think it's 7 lines, isn't it? 1, 2, yes, 7 lines. Unfortunately, it's gone over a page break. So you get this Philosophiae Naturalis written in the middle of it, and you can see that there's a PR at the end of one line, at the end of one page, followed by the PR at the beginning of the next. If you're used to reading books printed in that time, you'll realize that when you turn over a page, you expect to find the first word of the next page printed at the bottom of the one before. It helps you to read it. Cum vis ad centrum ellipseos tendens, and so forth. And there's my translation. English is Latin is rather a nice compact language, and so the translation takes up a little bit more space. Don't bother to read it; it won't make any sense to you because it refers to diagrams and bits which we can't see there. Right. So, but there it is in one sentence. It's a stunningly, it's absolutely great mathematics. It really is. Oh. So, I want to make two quick mathematical comments because some of you here aren't mathematicians. But first of all, I would just say that if you take, say, a more modern dynamical point of view, such as in Goldstein's classical mechanics, which was modern when I was young and isn't now, you get a far more sophisticated approach using variational principles and so on. And it eats all this stuff up and goes further, of course, rather easily. Rather more interestingly, for the mathematicians, I hope that you might recognize in going from an ellipse and its center to an ellipse and a focus, a conformal transformation. And the sharpest proof of the law of the ellipses is generally taken to be a proof using conformal transformations. And if you decompose that proof, you might find that Newton had got there first. Right. So now some slightly less mathematical comments. The three of them. We've seen two cases where we get an ellipse and a nice simple law. One way with the thing in the center when it's directly proportional, and one when the center of force is at a focus and it's inverse square law. What others are there? Well, an inverse cube law can also give you an ellipse. And more entertainingly, an inverse fifth law. But for an inverse fifth law, what you have to do is you have the sun here, or where my finger is, and you have the planet is going to move on a circle, which goes through the sun at an infinite velocity. So it will go around here, there'll be a bang when it goes through the speed limit, a flash when it goes faster than the speed of light, pre-relativistic mathematics, smash into the sun at an infinite velocity, and so on. And Newton, those are the only cases. And Newton finds them all. He doesn't prove that they're all, but he must have looked, he must have been. I'm just totally amazed that he should have thought of this. It's just so clever. Yes. Then there is the point of this isochronos pendulum. As I said, when you swing the bead, it's approximately the isochronos. That is to say, takes the same time regardless of the amplitude. However, there is a gentleman with a very, very fine beard who's doing the thing properly. Those of you who know about these things will realize that because the force isn't directly proportional, because angles and so on have turned up, it's not strictly isochronos, and so you need this. You need this wooden thing at the top, which is a cycloid. We'll come to do a bit more about cycloids in a moment, so you can see what they are, and which will cause the cord or the string to obviously to bend, and then it is, at least in theory, completely cycloidal. It looks as if you pull that handle, so beer should appear from somewhere, but I don't suppose that actually happens. At the top. It's not a very well drawn cycloid. At the top, those tangents should actually be vertical. Now, yes, so to show you a proper cycloid, what I should do is to produce a disc, which I haven't done, and attach a light to the rim of the disc, turn the lights off, and roll the disc along, and the little light on the rim will execute a cycloid. And the vertical bits will be when the rim is actually touching the table. Of course, that's upside down, so to get the proper thing, I would have to get it to roll on the underside of the table, which is the reason why I haven't actually done it. This was known to the great Huygens. We might even have a slide of Huygens. Yes, there's Huygens. I don't see. I thought I got his dates up, but I haven't. Never mind. There's the great Huygens, and here Newton, of course, is going to go one better than Huygens. He's going to put his clock in the basement. Now, gravity gets less as you go nearer the centre of the Earth because most of the Earth is pulling in the wrong direction. And as Newton proved, the force of gravity is then proportional to the distance from the centre. And it doesn't go downwards, it points towards the centre. So now your cycloid, instead of rolling my hoop along, or at least underneath the table, I should roll it under a curved table that is curved according to the radius of the Earth. And we can test whether this table has that property by just putting a drop of water on it. And, of course, if it's flat, the water should move to a point nearest the centre of the Earth. But if it's properly curved, the water should be all right. But anyway, there we are. So what we now have, we have a hypocycloid and an epicycloid. The one that we're really interested in is the hypocycloid, the thing underneath. Here, the big circle is the circumference of the Earth. The small circle is the circle that we're rolling along to get our epicycloid, and there's the point P. And Newton is proving then that if the gentleman with a beard uses an epicycloid and the thing is in the basement, then it will be absolutely perfectly correct, allowing for these subtle gravitational differences. Now, it turns out that if you make this smaller circle half as big, half the radius of the big circle, then the cycloid actually degenerates into a straight line going up and down. Well, Newton wasn't the first to think of that. In fact, I don't know if he thought of it at all. The first person to think of it was Nasir al-Din al-Tusi, or otherwise known as bin Muhammad bin al-Hassan al-Tusi, or sometimes known in the West just as Tusi. And there he is on a fine Persian stamp, to 1201 to 1274. There he is. And I'd say that pendulum clocks were the most accurate clocks available till about 1950, and they would operate to an accuracy of about a second in a year. And they were then replaced by quartz things. And nowadays, the definition of time has just been changed, hasn't it? I think it's now to within a second in the lifetime of the universe or whatever. But anyway. And the third point, which I will rather skip over, which is that Newton here is proving that if the planets move in ellipses and so forth, then it's an inverse square law. What about the converse? If it's an inverse square law, does it have to be a conic? And people were grumbling that he hadn't proved that. Well, they hadn't read the Principia for a start, because his third proof proves it the other way round. And it doesn't just do that. It solves the problem subject to calculating integrals for any force, any reasonable force whatsoever. But I suppose that his critics couldn't understand it. The fact that his first proof is adequate is a matter of the uniqueness of solutions of differential equations, and I won't go into that. Then one historical comment, which I think is quite interesting. There was a very famous American physicist, Richard Feynman, at Caltech, and he gave prestige lectures once a year to his physics students, high-profile lectures. And he was going to give one on Newton's proof of the law of the ellipses. Assuming, of course, and having announced that he was going to do this, he assumed he'd be able to understand Newton's proof of the law of the ellipses. So he looked at the first proof and found he couldn't. So he produced a brilliant Newtonian-style proof of his own. Why couldn't he understand it? He said it was because he hadn't got a sufficient training in the theory of conics. That I don't believe that for a moment. I give everything that you want about the theory of conics in an appendix to my book. It's very little. It's all completely obvious to him. The reason why was Newton's style of writing. It's proposition 11 of section 3, book 1. And the notation is taken over from proposition 10, which is in the previous section, and Newton doesn't bother to tell you. And, of course, neither of these two translations bother to tell you. So a really great physicist finds that he can't understand something which I could explain to a competent A-level student. It's a matter of Newton's style. Now, where have we got? Yes. So I'm now going to say a few words about Newton's calculus. As is well known, there was a prolonged and ill-tempered struggle between the supporters of Newton and Leibniz. There's the great Leibniz. He was a splendid man. the argument was as to which of them invented the calculus. Neither of them invented the calculus. The fundamental theorem of calculus was known to Barrow, who was Newton's predecessor in the Lucasian chair of mathematics at Cambridge. He wrote a whole book about it. So that neither of them invented the calculus. Everyone was busy inventing it. But Newton was the incomparable expert. But I will say, while Newton's notation is very rarely used and only in special circumstances, Leibniz's notation is used everywhere. And Newton sort of believed that when God created the universe, first of all, he produced some coordinates. And then he sort of filled it with stars and all the rest of it. Whereas Leibniz took the view, which is now, I believe, completely accepted by physicists, that in fact that there aren't any coordinates built in, and that in some still unknown way, the laws of motion are guided by all the distant stars and galaxies. You see, it's a matter. Well, when something rotates, you can tell it rotates. I mean, its hair flies out sideways. But how does it know it's rotating? Newton says, well, it's rotating with respect to these God-created coordinates. But Leibniz and Mach say, no, it's rotating with respect to the distant galaxies. And somehow it knows that that's what it's doing. Right. Anyway, but of course, although Newton believed in Cartesian coordinates, they're called Cartesian because they were invented by Descartes. We better have a picture of Descartes in case someone doesn't know what he looked like. There we are. The Principia can be most of it can be read as an attack on Descartes' astronomy. One of the things that Descartes asserted was that if something is addressed, if it's addressed with respect to its surroundings. So I take a nut and throw it across the room, and the kernel of the nut is addressed because it's addressed with respect to its shell. Newton said, "Oh, this is just nonsense. Of course it's not addressed. Look at it." What Newton didn't realise was that Descartes needed to have a formulation by which the earth is at rest as required by the Inquisition. He was required to state that the earth was at rest, and it is at rest with respect to its atmosphere. Well, anyway, elementary calculus is generally concerned with finding the area under the curve and calculating gradients and maxima and minima and so on. It's much more interesting and difficult problem when the answer is not an area or not a number, but a curve. And Newton, in working out the best shape for a ship, was the first serious solution of a problem using the calculus of variations, which is a lovely problem. He was more famous for solving the Brachistochrone problem, which hang on, that is oh, I'm sorry, I've got these. Yes. Hang on, I think I've got these slides. Yes, now, yes, I think that's a lovely slide. I just took it out of Wikipedia, and look, it worked. I think that's stunning. Isn't that clever? The problem is this: you're trying to get something a bead to slide from the top point to the bottom point as fast as possible, and the idiot solution is to just produce a straight line. An alternative is to let it drop immediately to get maximum speed and then go horizontally, which you see is faster. But the best solution is, again, our friend the cycloid. There it is. You see, it beats the lot of them. Isn't that clever? And what actually happened was that Newton was sent the problem on the 4 p.m. on the 29th of January 1696, according to the Julian calendar, and had solved it in 12 hours. That was 4 a.m. on the 30th of January. So he was up all night and solved it. And he posted the solution anonymously, with only a few details of how he did it, to Johann Bernoulli, who recognized at once who had produced this, saying, com ex ungue leonem, or as I would recognize a lion by his claw. He's writing in French and quoting a Greek simile in Latin. According to the Wikipedia article, says that this wasn't Bernoulli giving him the ultimate accolade, but I don't agree. He didn't say I recognise it as I recognise Mrs. Jones by her hat. It was the lion by his claw. A far more important contribution was the Navier-Stokes equation, which is a partial differential equation which describes the flow of a viscous fluid under reasonable assumptions. And also Stokes' equation. Many of you won't have heard of Stokes' equation, which is an easier partial differential equation for solving the same problem. The reason that Newton pursues this topic is it's part of his attack on Descartes' theory of vortices. Descartes said that the planets are whirled around the sun in the same way that the leaves are whirled around in a puddle, or possibly water coming out of the bath or whatever. I mean, Descartes has just had a look, so yeah, that's what's going on. Whereas Newton attacks the thing with very serious mathematics. He destroyed the theory of vortices in 6 different ways. And in this one, he supposes that empty space is filled with some stuff, the water in the pool, which is making the planets whirl round. And he's produced the Navier-Stokes equations, and he's now got to solve them. When it comes to partial differential equations, I want to say as little as possible about it, but you have to have boundary conditions. Here, the boundary conditions are that the vortex at the sun's surface is swirling around with the sun, and when it's got to infinity, it's pretty much addressed. And then, how does the vortex spin when it's got to a stable state? The fact that it does come to a stable state is one of these clay mathematics problems. There are $1 million or whatever riding on a solution, and one of the 7 most important problems in mathematics. Newton does not attack this. He merely produces the stable, he just wants to produce a stable solution in the case of the sphere, which is an extraordinarily difficult problem. Well, again, if you've got a difficult problem, start with a simple one. So instead of having, replace the sun by an infinitely long cylinder and let the cylinder just rotate about its axis, okay? It just spins around its axis. Now, it's pretty obvious, isn't it, that the vortex is just going to go in circles around the cylinder, and you've got to work out to what extent the velocity gets less as you go further out. You go further out, further from it, it's going to go so closer, it's going to go faster. And Newton worked out that the angular velocity was inversely proportional to the distance. You double the distance, you halve the angular velocity. And then he goes on to solve Stokes' equation. You have to simplify it a bit, for a sphere rotating. And now, of course, if the sphere is rotating like this, it will get, the velocity will get less when you go out in that direction, and also when you go out in this direction. It's the sideways direction which is more interesting, particularly when you're thinking of the sun and the planets, which go around in a single, where it is more or less two-dimensional. And he found that it's proportional to the inverse square. Unfortunately, he made a mistake with both. With the cylinder, it's inverse square, and with Stokes' equation and the sphere, it's in fact inverse cube. But of course, Kepler's third law tells us it's proportional. It actually decays to the power 1 minus 1.5. So that although Newton got the details right, the thrust of his argument was correct. It's not so very easy to get this right. It was finally put into a proper state by Stokes in 1845. And before reaching this happy state from Newton's first attempt, it had been through the hands of Daniel Bernoulli, Euler, Laplace, Gauss, Navier, Poisson, Green, Saint-Venant, and finally Stokes himself. It wasn't an easy problem. In another stroke of genius, how am I doing? Yeah, I'm fine. He calculates the speed of sound in air. Quite something to say, well, I can calculate the speed of sound in air. He got that wrong as well. He underestimated it by 15%. The error is due to the fact that he assumed that inevitably the sound waves were isothermal, where in fact they're adiabatic. The sound waves, as I'm talking, I'm heating up the air. I hope not oppressively, and it's the sound wave heating the air which produces the error. Laplace worked that out 100 years later. But a question for you all: how do you imagine that Newton measured the speed of sound? To calculate it, you solve a partial differential equation. But how do you measure it? You haven't got a very convenient watch to hand. Yes, I've just got time to this. I'm now going to say something about Newton's attack on the motion of the moon, which was somehow the central question of the Principia. Because, in particular, to justify his law of gravity, he's got to get the sums right. And the problem now is, I will mention the apple. You can work out what the acceleration due to gravity is at the Earth's surface. You drop an apple and see how long it takes to fall. Or more sensibly, you get a pendulum to swing. But anyway, it's the same as an apple. Now, if it's an inverse square law, the moon's 250,000 miles away. I think that's right, isn't it? And you can work out what the force should then be for it to go round the Earth. And you work it out, and damn it, it doesn't fit. It's quite a near fit, but it doesn't really work. It's not, the error is just too big. Of course, the moon's orbit is very complicated. It's not precisely circular. It's circular enough, and the error is just too big. What has gone wrong? What has gone wrong? Any genius, any Newtons here? What has gone wrong is this. You don't have the Earth here and the moon going round it. The Earth and the moon go round their common centre of gravity, or barycenter, if you like, you understand these technical terms. So where is the centre of gravity between the Earth and the moon? How do you work it out? Well, you know how far away the moon is, you work out how big it is. What is its density? You've got to compare the density of the moon with the density of the Earth. It's only the relative density that matters. Newton worked out the density of the Earth by just sort of tapping his foot on the ground and said, yeah, it's somewhere between 5 and 6. Actually, it's 5.5. but how do you compare? You can compare the density of the sun with the density of the Earth because they've both got satellites. The moon goes around the Earth goes around the sun, and you do a sum, and you can work out, and the Earth is very much denser than the sun. What about the moon? It doesn't have a satellite. But to compare, because you can compare the density of the Earth with the density of the sun, to compare the density of the moon with the density of the Earth, it's sufficient to compare the density of the moon with the density of the sun. Right. Well, there's a question for you. You've got about 5 seconds for it. How would you compare the density of the moon with the density of the sun? One word, please. I hear you all say tides. The moon produces a tide, and the sun produces a tide. And because they both look about the same size when the same as angular thing, they look the same size from the Earth. If they were the same density, the sun's tide, the solar tide, would be as strong as the moon's tide. But it's not. The moon's tide is stronger. So now, in order to compare, using tidal theory, the density of the sun with the density of the moon, you have to work out how tides work. I think Newton was perhaps the first person to work out why you get a tide approximately every 12 hours instead of every hour, every 24 hours. I mean, you've got the Earth here and the moon here. You expect a high tide over here. But why do you get a high tide on the other side? There's a little exercise for you. And there are enormous complications which Newton produces with the tide. Astronomical things of all kinds. It's a hugely complicated business while he's working out what the density of the moon is. He didn't get a very accurate answer, but he put an enormous amount of genius into it. But his entire tidal theory was unfortunately destroyed in the Cohen-Whitman translation. I shouldn't carry on like this. But what does semester mean? Well, semester is month, and it either stands for sex, meaning 6 in this context, or semi, half. So it either means a fortnight or 6 months, and it can mean both in Latin. And you'd better get it right, because otherwise the whole theory goes up in smoke. Now, yes, good, okay. So I'm doing fine for time. Where we've got to just sort my notes out. Yes. The other problem with the moon's motion is the three-body problem. Where is the moon going to be at a particular time? And this was a topic which people then were very concerned with, because it would help with the navigation of ships. When Sir Cloudley Shovel sank the entire British Navy, it was because he didn't know where he was, obviously, and there was enormous enthusiasm for producing a proper ephemeris, being able to work out where the moon should be at a given time. Actually, of course, it was Harrison's clocks. Harrison was a contemporary of Newton, and he produced these stunning clocks, and absolutely brilliant clocks, which and they're the Harrison 3, which you can put on a ship and work out exactly where you are. But Newton was producing this theory of the moon's motion, three-body problem, enormously complicated. He made a mistake which you will understand if you understand the mathematics of a gyroscope. He made a mistake there, and he realized it had gone wrong, but never managed to work out why. But it's just complexity on complexity, of course. And he never actually, in the Principia, gives you instructions for working out where the moon is going to be. But he produced a little pamphlet, first of all in English, and then translated into Latin so that people could read it. And this pamphlet it's very interesting. It seems to owe it's quite something to Horrocks, who was a famous astronomer. He died at the age of 23 before Newton was born. And it's very interesting. He's using cycles and epicycles, which go back to Apollonius of Perga. There are a lot of Apollonii, you have to get the right one. But which you might say were the first two terms in a Fourier analysis. I don't know. Anyway, the way Newton's attack on the moon was indecisive, heroic, and led the way forward. There's still no proper analysis of how Newton's theory fits in with modern theories, which are done differently. I should be winding up now soon. So the first edition of the Principia ends with a stunning attack on computing a comet's orbit. It's done in successive steps, and in the first place you work out the projection of the comet's orbit onto the ecliptic plane. So you've got the Earth and the Sun and the projection of the Earth's comet all in a plane, so you can draw it on a piece of paper. You'll see at the bottom right there's a curve which contains the letters capital T, lowercase t, and the Greek Tor. T for terra, the Earth. The Earth is moving across that curve. And then you see three lines going, one through T, one through straight lines, one through capital T, little t, and capital Tor. And they are the lines of sight when you took the observation. You see the comet, but you don't know how far away it is. And these are three observations of the comet. And so what you do is you guess how far away it is. And then you make another guess, and then there are various things which should coincide and don't, and you fiddle around and do some clever stuff. Newton did this from the real data. on a piece of paper, and he is working to 1/100 of an inch. Halley did it by calculation, which was more effective, hence Halley's comet, because, of course, if the comet's going in an ellipse and you work out the data, you can tell when it's going to come back. And Halley worked out when it was going to come back, and 73 years later it did come back. But of course, you could also trace the historical record backwards. And it was traced back to the Anglo-Saxon Chronicle and the times of ancient Rome. When you know what the period is, that you can do this. Then, that was the end of the first edition. The second edition, well, people complained with his theory of gravity that he hadn't said why the inverse square law is satisfied. Why is it satisfied? And Newton was really not very pleased with this question, particularly when people started producing ridiculous explanations as to why. So he wrote the great and final general scholium, in other words, a general commentary on his book, which starts off with his attack on Descartes' theory of vortices. The hypothesis of vortices is pressed with many difficulties. Understatement, actually. And then he sets forth his theological stance. Why is the universe as it is? In his theological stance, he uses a different voice. He's speaking with great passion and belief. It's not mathematics any longer. He was a great theologian, a very great theologian. And he is talking now about what is the nature of Godhead. What is it to be? What is nature of Godhead? What is it that makes God God? And he says that that the essence of Godhead is dominion. It is because God has dominion that he is God. Now, the few will have recognized what is going on here, and few people did. There was a great division in Christianity between Arianism and the Orthodox beliefs, particularly Athanasius. And this was a tremendous cause of dissent. And Newton was a crypto-Arian, which was more or less illegal in his time. More or less illegal. And he didn't want to let it out. But, you see, why Christ is the Son of God, but he is not God because he lacks dominion. He didn't put in that extra bit. You had to read it behind the lines. And also, Newton was like that. He also then says, as far as his metaphysical explanations are concerned, hypotheses non fingo. I have left that untranslated. I assume no hypotheses. Great passion. I assume no hypotheses. All this rubbish. No hypotheses. The Principia is littered with hypotheses, numbered and labelled, hypothesis 1, hypothesis 2, and are duly assumed. However, when he's writing his mathematics, he means one thing by hypothesis. And when he's writing the general scholium, he means something else when he writes hypothesis. He is always using the same word with different meanings. He writes the letter to Coates, who is the editor of the second edition, explaining what he means by hypothesis in this general scholium. But his hope, the Principia is riddled with far more serious ambiguities than that. But Newton's hope that the reader would be able to distinguish the various ambiguities from the context have, I'm afraid, been disappointed in various translators who didn't actually understand the text. But enough. Thank you.
Was 2 years without you, is it? Thank you very much, Charles, for this fascinating talk. And perhaps you want to say that there is a special offer here.
Yes. Well, it is self-explanatory, but there's a copy of the book, and if you want to get it for 30% off, it'll still cost something. You can it's explanatory. You can see what you have to do.
Yes, there is a QR code here. If you can. But now we have time for questions. So as usual, raise your hand.
Hi there. Great talk, by the way. Obviously, Isaac Newton, a great genius, and these people do come along from time to time. You know, when he measured the speed planets going around the sun, it didn't work out quite right about Venus, I believe, and he didn't actually twig what Einstein actually worked out later with his theory of general relativity. And it's just amazing that the mind of Newton couldn't twig what Einstein, worked out about light and matter and space and time. And I've often wondered what kind of conversation they would have had if they were together.
Yes.
At the same time. That would have been incredible. I think.
Yes, I'd love to give you the conversation, but I'm afraid it's a very interesting thought. But it's a very interesting question, but I don't think I can answer it. Of course, there was a question as to whether the inverse square law was precise, and of course, there were problems with the orbit of Mercury, which were discovered far later. What happened? But the general thing was this: you've got the sun, and you've got your planet going around it in an ellipse with the sun at the centre, and the major axis of the ellipse stays where it is. But if you vary the inverse square law ever so slightly, the ellipse will begin to spin. And the fact that no discernible spin was observed meant that it was more as precisely as one could tell was the inverse square law. And I believe that when it was seen that the orbit of Mercury wasn't quite behaving itself, the first suggestion was that it wasn't quite inverse square, but inverse 2.03 or something. And that was wrong. Whether it's in Newton, the speed of light was calculated in Newton's time. Not calculated, of course not, it was measured. But you see, from Newton's point of view, you've got these Cartesian coordinates. And once you've got these Cartesian coordinates fixed, then you do have absolute velocity. So that he can't, so a relativistic point of view was completely alien to him. Leibniz is the one who might have thought of general relativity, because he doesn't insist on Cartesian coordinates lying there.
This is probably a rather trivial question in a way, but in the last 25 years there's been 2 translations of Newton's Principia.
Yes.
The other one was 250 years ago. Why do you think there was such a gap between the 2?
Oh, what a nice question. There have been, yes, in the meanwhile, there have been 11 translations of Gogol's Dead Souls. Yes, it's an interesting question. It's a dangerous thing to do, in that a high proportion of the people who have had a go at translating it have died before the translation came out. It's a long and arduous exercise. I must say, I started doing it just as a hobby, and then it was suggested I should take it seriously. I was nervous that I would just get stuck with the astronomical bits towards the end. There are very serious professional full-time Newtonian scholars who've just given up on the astronomical stuff and just concentrate on other aspects of it. So yes, it is quite difficult to. It's not all that difficult, but there's a lot of it. Papers have been written about individual propositions in the Principia. It's interesting. I think that the historians, on the whole, have been unaware of how inaccurate these translations are in making mathematical mistakes. You see, one of these howlers is you've got in Latin. You tend to leave out articles. So man bite, you don't say a man bit the dog. You might just say man bit dog, and you have to. Of course, you can make it explicit, but there's a tendency to leave things out. And there's an argument with a parabola, and then parabola appears again. Is it a parabola or is it the parabola? Is it the same parabola? Well, because of a failure to cope with another ambiguity, Cohen and Whitman get it wrong. So you get a total nonsense, with one parabola having become two parabolas. Whereas what made them lose their temper with the Mott Cajori translation was that one professor had ridiculously become two professors. But it's much more serious when one parabola becomes two parabolas, because the whole thing turns into nonsense. And in Latin, you can, as is written, then you have the same word is used for the sum, the product, and the integral. Yeah. So you have to work out what it meant. And Cohen and Whitman, for some reason, which I was taught not to do this when I was about this high, will translate words into the etymologically closest. So they pronounce velocitas as velocity and celeritas as speed. Well, Newton is a great one for elegant variation. He usually uses velocitas, and sometimes he says, I'm bored with this word, let's use celeritas instead. There's no suggestion of meaning. But velocitas, it never means velocity in the technical sense. Sometimes it means speed. Sometimes it means acceleration. Sometimes it means speed with a sort of sign attached to it. I mean, it is quite a prolonged effort, quite a lot of effort to translate. Various people have translated bits of it. But no one has actually gone through the whole thing. The trouble, of course, if you're going to translate the whole thing, you can't say, well, I don't like this bit. You've got to go through the whole. It is a struggle. I mean, it did take me 20 years. Not full-time work, but it was 20 years. And I think, I dare say that one could, if I had to learn Russian and translate Dead Souls into English, I might do it faster, but I don't know.
So could we bracket the Principia along with Marx's Das Kapital? The only people that have really read it are the printer. No, it has been discovered, apparently recently, that rather more people read and understood the Principia than had been realized. Certainly all the top mathematicians read it and produced commentaries and so on. There was, I'm sorry to say, a version produced for women and children. Oh dear. And du Chatelet's translation was by far the greatest for a long time.
You alluded earlier, or just now, to the complications that arise from ambiguities of vocabulary.
Yes.
We, of course, have the advantage of understanding these concepts with modern vocabulary which resolves those ambiguities.
Yes.
Do you think that ambiguity was one of the problems for lack of reception of the book when first published?
That's an interesting question. The other source of ambiguity or difficulty in the Principia is Newton's insistence on using arguments in Euclidean geometry rather than using the sort of coordinates of the sort of algebraic way, which also makes it difficult.
I must say that, that reading the Cohen-Whitman translation, I mean, I know I come across a couple of mathematicians who set about reading it and just gave up because it was too much of a struggle. I think there are all kinds of things that make it difficult. So Newton was brought up under the shadow of Cicero. So you get these great, long, involved sentences. There are, and of course, if you're translating it, if you can either decide to make it as obscure as Newton did, or you can try to produce a translation which can be understood. And if you produce a translation which can be understood, the historians say, this isn't a translation, it's nothing like what Newton wrote, I can understand it. So yes, you've touched on a difficult thing. I mean, I've tended to, on the whole, to keep reasonably close to what Newton wrote, and then in the commentary, it's about 40% commentary, and then, as it were, to rewrite it and explain what's going on. Newton's view was that people didn't understand it because they weren't good enough at geometry, but I don't know. But it was read quite a bit, apparently. Yes, copies turning up which have been read and referenced and so on. Yeah. I haven't read Das Kapital. Has anyone present read Das Kapital? Bits of it. Bits of it. Well done. So I think your point about Das Kapital has been pretty well made. Yes.
Yes. Concerning the inverse square law, the gravity law, there was a well-known dispute between Newton and Robert Hooke about the origins of the inverse square.
Correct.
Is there any allusion to that in the Principia?
Well now, you see, Newton's, yes, in a sense. The allusion is that Newton decided to make no reference of Hooke at all in the Principia and just wipe him out. He also destroyed all portraits of Hooke that he could find. However, his editors insisted that Hooke should at least get one mention. But yes, Newton, of course, was very irascible, and Hooke's job as an experimental officer for the Royal Society required him to demonstrate, I think, 4 new results every week. They didn't have to be new to Hooke, but they had to be new. And so Hooke was frightfully busy producing new results and didn't have much time for going into details. And Hooke was nothing like as strong as Newton when it came to mathematics, nowhere near. But yes, I think, but Hooke has claims to the inverse square law, and so have various other people. I mean, it's very easy to say, well, I think it's an inverse square law, common sense, and this, that, and the other. So there are various claimants to it, yes.
Thank you very much for the lecture. You mentioned about the barycenter, and he was working on, it seems from what you were saying, 2 bodies interacting. Does he actually go into anything as complex as the solar system as known at that point with the Sun and right up to Saturn?
With the Sun and...
Right the way up to Saturn, so all those interacting bodies working together?
No, he realised that the 3-body problem nearly killed him. And he certainly wasn't going to go as far as 4. I mean, after all, you see, with the Sun and the Moon, he's just considering a 2-body problem at that point. You just got these two. I mean, he's leaving out the Sun. He's just considering the Earth and the Moon spinning around their barycenter. So that is just a 2-body problem, which of course he solved without any trouble at all. You just have to work out where that barycenter is. Yes.
Other questions?
Thank you, and congratulations on completing the translation. Over your 20-year translation, Did doing the translation change the way you thought about mathematics?
What an interesting question. It didn't have any effect on my own mathematics. Obviously, it taught me quite something about the development of mathematics. I think that of course, Newton is not the only great mathematician, and obviously, if you're a mathematician, you tend to find yourself reading the works of various mathematicians. I would love to say that Newton somehow inspired me to great heights, but I think that would be self-delusion.
Other questions?
Was using Euclidean geometry as means of proofs in Newton, was it caused by him trying to make more rigorous proofs, or why do you think he was using geometry as proofs?
That's a very central question. Yes, to what extent was Newton trying to produce rigorous proofs? You see, Newton is such a complex character, and he faces in opposite directions the whole time. I sometimes think he is capable of having two contradictory believe two contradictory things at the same time. His formal position is this: all mathematics should be written should be based really on Euclid's geometry, and with complete and full rigour. In the same way that you and I believe that all mathematics should be written in terms of first-order predicate calculus, but it is someone else's job to carry out the actual translation, because it will then be fairly unreadable. And so in a sense, this is what he believed. This is very limiting. What is a real number for Euclid? Well, it is the ratio between two lengths. That is what a real number is. When you multiply two real numbers, you're now comparing two areas. If multiplying three real numbers, you're comparing two cubes, and you can't multiply four real numbers together. Whereas Newton will use power series with fractional indices, and in fact irrational indices. He will do anything. But in principle, he wants things to be based on Euclidean geometry. On the other hand, particularly in the context of the calculus dispute, he says, although it should be done in terms of geometry, actually, I did it all by calculus. And what is more, the ancients used calculus as well, and then translated it into geometry. So he is facing in all kinds of different directions. Obviously, Newton did not have a proper definition of continuity and limits. But I would say that I think that he is on the side of really tough and rigorous proofs. And sometimes when he's accused of assuming a result without a proof, I don't think he's necessarily assuming the proof. For example, he works out the shape of the Earth because it's spinning. You take a sphere of fluid because held together by its gravitational field, and you spin it, and it's going to swell out of it, isn't it? Well, exactly what shape is it going to be? Well, it's going to be, it's an ellipsoid, okay? So you take an ellipse and spin it around. And he works out how much it will swell out, what is the ratio between these two numbers. But people say, well, it is an ellipsoid, but he never proves it. I think he's just finding the ellipsoid of best fit. But yes, he is on the side of rigor. Yes, very much. Yes.
Other questions? Maybe just a short one. When you 20 years ago started this work, how you decided to start this kind of journey? Why did you decide to do that?
Well, what happened was I'd acquired a copy of the Principia, and it was an edition due to Corrier and Cohen, which is just the actual Latin, And then I came across, and then I saw this, the Cohen-Whitman translation, and I thought this is a complete disaster. You can't translate it like this. It won't do. And so I said, well, let's see if I can do any better. And it sort of grew like, was it Topsy that grew? Or so anyway, it just grew like something that grows. And I was encouraged to take it seriously, and so it happened. I certainly didn't set about it imagining that I was going to occupy so much of my life and actually get published, but that's what happened.
Thank you, Charles. Thank you very much, Charles, for your talk. To everyone who came to our first face-to-face public lecture, I just tell you that you exit the building, you might enjoy to see flowers on 3 small apple trees. Those, in fact, kind of clones, basically. They are trees from cuttings of actual Newton tree, which we believe is still alive in his hometown in Gottfried Manor. So you can photograph yourself in front of Newton trees. And we hope we will continue with this face-to-face public lectures in future. In the meanwhile, those who know, we are also continuing our online talks. The next one, in fact, will be in about a month's time, on 27th of May, will be our usual astro chart. Thank you very much. Charles, again, thank you very much.